Hi everyone, in my today's session I'm going to explain about the structural design pattern called composite pattern. Okay, so in software engineering the composite pattern is a partitioning design pattern basically. Okay, so the composite pattern describes a group of objects that are treated the same way as a single instance of the same type of object and its group of objects. Okay, the intent of a composite is to compose objects into tree structures to represent part whole hierarchies. Implementing the composite pattern lets clients treat individual objects and the composites or compositions uniformly. Okay. So, what problems can the composite design pattern solve? A part whole hierarchy should be represented. Okay. So, what problem this particular pattern is going to solve? First of all, a part whole hierarchy should be represented so that clients can treat part and whole objects uniformly, basically. So, no discrimination. Okay, a part whole hierarchy should be represented as tree structure. Yes, this can be achieved through tree structure itself. Okay, because even the leaf node and the complete branch or the complete tree will have some functionality in common. Okay, so tree structure is the preferred representation here. When defining part objects and whole objects that act as containers for part objects, client must treat them separately, which complicates client code. Okay, what problem we have seen is when defining part objects and whole objects that act as containers for part objects, client must treat them separately. Okay, when we treat these things, both the part as well as whole separately, right, that will complicates the client code and it is not unit testable. Okay, we will add unnecessary complications. So that's why when we implement this design pattern, these two things should be addressed properly. Okay, what solutions does the composite design pattern describes? Define a unified component interface for both part, that is the leaf object, and the whole, the composite objects. Okay, so this will get the discrimination out of the part and whole structures basically. Okay, so this component will contain a uniform operation which is same across part as well as whole. Okay, now individual leaf objects implement the component interface directly and the composite objects forward requests to their child components collection. Okay, the composite objects basically maintain a list of leaf objects and whenever a call comes they will basically forward those calls to the child components. This enables clients to work through the component interface to treat leaf and composite objects uniformly. Leaf objects perform a request directly, whereas a composite objects forward the request to the child components recursively downwards the tree structure. Okay, again you can put some filters, you can basically enhance as per your requirement. Okay, this makes client classes easier to implement, change, test and reuse. This is the most important thing. By implementing this, it's very easy to implement the classes, and yes, it will be very easy to change them, test them and reuse them. Now motivation, which is I already explained. When dealing with the tree structure data, programmers often have to discriminate between a leaf node and a branch. Okay, this makes code more complex and therefore more error prone. The solution is an interface that allows treating complex and primitive objects uniformly. In object oriented programming, a composite is an object designed as a composition of one or more similar objects, okay, all exhibiting similar functionality. This is known as a hazard relationship between objects. Okay, the key concept is that you can manipulate a single instance of the object just as you would manipulate a group of them. Okay, the operations you can perform on all composite objects often have a least common denominator relationship. Okay, so for example, if defining a system of portrait grouped shapes, okay, so if defining a system of portrait or drawing grouped shapes on a screen, it would be useful to define resizing a group of shapes to have the same effect, okay, as resizing a single shape. So when to use? Composite should be used when clients ignore the difference between compositions of objects and individual objects. Okay. If programmers find that they are using multiple objects in the same way and often have nearly identical code to handle each of them, then composite is a good choice. Okay. It is less complex in this situation to treat primitives and compotitives as homogeneous. The UML class diagram for the same. Okay, you can see I will specify that uniform interface called I component and specify that uniform operation or identical operation done by the leaf node as well as the composite or group of objects. Okay, so this is the uniform interface I component which specifies the operation method which is uniform across both the leaf and composite. So the leaf will implement that operation and implements or executes it directly, whereas composite basically implements that operation, okay, in such a way that it is applied on each and every leaf node which is basically contained by this component. You can see here parent, this is the component which is basically zero or more, and it is a child, it's basically aggregation inside this component. So there will be a collection of components in this composite. And apart from that, the composite specifies the additional behavior like adding a leaf, removing a leaf, and getting a child or a leaf by its ID or something. Okay, a pretty straightforward class diagram. Okay, I have already explained what all these things are. Okay, there are two design variants for defining and implementing child related operations like adding, removing a child component to or from the container. Okay, so design for uniformity. Okay, child related operations are defined in component interface. Okay, this enables clients to treat leaf and composite objects uniformly. Okay, what they are saying is in case of design for uniformity, what they will do is they basically put this add, remove, get child, all these things into this component interface itself apart from that identical operation. Okay, so this way child related operations are defined in the component interface. This enables clients to treat leaf and composite objects uniformly. But type safety is lost because clients can perform child related operations on leaf objects. See here, leaf directly performs an operation and leaf doesn't maintain any collection. Okay, if we think in one business requirement or in one perspective of the requirement, leaf doesn't contain any collection, it's a node itself. Then what is the use of implementing add, remove, get child? Okay, so you won't achieve the type safety in the design for uniformity when you introduce all these add, remove, get child methods to the base or the uniform interface over here. Okay, so that's about the design for uniformity and design for type safety. Child related operations are defined only in composite class. I think this is what we are going to do. Child related operations are defined only in the composite class. Clients must treat leaf and composite object differently, but type safety is gained because clients cannot perform child related operations on leaf nodes. Okay, so they say that okay, in case of design for safety, what you will do, it will look like this UML diagram. All child related operations add, remove, and get child are defined at the composite level, not at the leaf level or at the uniform interface level. Okay, okay, so we need to go with this particular approach, guys, because it's pretty straightforward. Okay, your leaf doesn't contain any collection. It's a leaf itself. It's a atomic node itself. So it should not do all this add, remove, get child related operations. But if you come up with a business requirement where even you want your leaf to become a composite when the requirement changes, then in such cases, what you can do is you basically have to put that collection of leaf inside this component. That's the component itself. Okay, and then specify all these operations over here so that both will be uniform. Okay, a leaf node can turn into a branch at any instant of time whenever you add a child to it. Okay, so that's what is all about. And the composite design pattern emphasizes uniformity over type safety. Its main goal is uniformity. Okay, so do remember that. So I have gone with the approach of type safety here because I know in my case I don't want my leaf to become a branch or a tree itself. So my leaf will be leaf itself and my composite will contain a group of leaf objects. Okay, both options are given to you, design for uniformity and design for type safety. It's up to us based on our business requirement. We have to implement any one of this. So let's move on to demo now. So I have gone with the approach of one mistake I did. I have gone with the approach of design for uniformity only, guys, because I have not moved the add, remove, get child to my uniform interface. Okay, I have kept it at the composite level only. That way I have ensured the uniformity across leaf and composite. Okay, my leaf will not inherit any add, remove, or get child from here or implement all these methods from this interface. Okay, it will contain operation and this composite will also contain the operation. Okay, so that's all said. Now go to demo. So public interface I component. Let's adhere to our UML diagram. This is my interface I component which specifies one operation which is display price. Okay, a very trivial example I have taken. for demonstration. Then I implement my leaf class now, public class leaf, this one. Okay, my leaf is a independent node or leaf itself. Okay, it doesn't have anything. So very simple, price name, and I'm implementing the method display price. So the component name is name and its price is price. Pretty straightforward. Okay, class which implements my contract I component. Then comes the composite. Now public class composite also implements I component, but look at the way it is implemented. Okay, this component has a name, this composite has a name, and then a list of I components. Okay, because it's a composite, it will contain a n number of I components. Okay, so list of I components, and then add component. I have introduced only a add component method, so you people can put a remove component to remove a component from this collection and get a component by its id, up to you, or by its name. Okay, so add component and then display price. I have implemented the I components only single method, which is a display price, but see the way it is implemented. I iterate over each and every component in my collection and I will call the display price method. Okay, that is the functionality of a composite. Okay, and look at the functionality of a leaf. Directly display the price, but this one iterates over the components and displays the price for each component. So let's go to the main method. Very simple. Okay, first of all, I create some leaf nodes. Like I will take an example of our computer system. Okay, our system itself, our computer itself. Okay, so hard disk. Okay, name, its price, RAM, name, its price, CPU, mouse, keyboard. Okay, I created the leaf nodes first. Okay, then creating the composites. Okay, now I'm going to create the composite or the container object which will contain this hardware component. So motherboard will contain, okay, the motherboard will contain RAM and CPU. So let's create a motherboard, cabinet which contain entire system, peripherals, your input output devices, and the complete system, the computer. Okay, so see, motherboard dot add component CPU. Okay, because motherboard contains CPU and motherboard component contains RAM, so I'm adding these two. Then cabinet dot add components motherboard, because our motherboard and hard disk is inside a cabinet. Okay, a desktop computer example is okay. So peripherals contain mouse and keyboard, and then computer contains the cabinet, peripherals, everything. And when I make a call to computer.display price, it will iterate over each and every component or a group of components and displays the prices and their names. So let's run this program. Okay, and I can see the individual things also, individual component name and price also. So let's run this program. Control. So I run the program, you can see the output. When I called display price or the computer dot display price, price of computer composite components. Can you see? It contains a component name CPU, it contains a RAM, it contains hard disk, mouse, keyboard, because it's entire system. It's a whole composite. Okay, it's a whole, basically the whole object. Now price of keyboard child or leaf component. See, keyboard, the component name is a keyboard and its price is 2000. Now price of cabinet composite component. Now see, what all things cabinet contains. Cabinet contains your CPU, your RAM, and your hard disk. Can you see how it is properly rendering the name and output at the component, sorry, at the leaf levels. Okay, and also at the composite levels also. Okay, so that is all about the composite design pattern, guys. I hope you people understood the concept, and I hope you people will apply in your day by day design activities. Thank you for listening, and have a nice day.